Shubhangi Saraf from here.
So I'm going to be talking about testing of sparse linear codes. And all this work is joint work with Swastik. Okay, so let me define what a locally testable code is. So say my universe is f2 to the n, and so my code C is just some subset of these points. And I'll be talking about linear codes. So a linear code is just a linear subspace. So I'm thinking of C to be a linear subspace. Okay, and so I say that C is locally testable. So C is locally testable. So there exists a tester T which behaves as the following. So the tester gets as input some point in f2 to the n. Okay, so the tester will see some n bit long string, and the tester, by just efficiently querying it in very, very few coordinates. So let this be the received word. The tester, by querying R in very few coordinates, so say in constantly many locations, it needs to decide the following. So if the received word is actually a code word, then we want the tester to accept. And if the received word, so the distance of the received word from the code is a lot. So say if the received word is at least epsilon far from every code word in Hamming distance, then we want T to reject with some probability, with some noticeable probability. Okay. So for any code, if you can design a tester which works like this, we call the code a locally testable code. So again, so you might get a, say, a corrupted code word is some string. By looking at it in very, very few locations, you want to decide, are you a code word or are you far from code words? And maybe the best studied in the classical code which we know, which is locally testable, is the Hadamard code. Okay, so how does the Hadamard code look? So the length of the code here, let n be 2 to the n. The Hadamard code is a linear subspace of f2 to the n. So the generator matrix looks like the following for the Hadamard code. It's an n by 2 to the n matrix. And if you look at the columns xi, there are 2 to the n columns. So each column is an n bit string. There are 2 to the n such columns. So for each x in f2 to the n, you have one column representing it. So all the elements of f2 to the n represent some column out here. And so what do the code words of the Hadamard code look? So if you have a message m, the encoding of the message m is just m times g. Right? This is like m times inner product with m with x1, m with x2 to the n. Right? So the code words, so the code word looks like the linear function m times x evaluated at all the points of the domain of f2 to the n. Okay, so these code words are, this is basically the truth table of some linear function, of the linear function m times x. So the code words of the Hadamard code look like two tables of linear functions. A received word in this space would look like something like R1, R2 to the n. This is basically some linear function. Okay, so the code words are linear functions, received words are some functions defined in the entire domain. And so locally testing the Hadamard code is exactly saying query the received word in some locations and decide, is the received word a linear function or is it far from every linear function? Okay, so locally testing the Hadamard code is exactly the question of testing linear functions. So then let me define what this question is. Okay, so linearity testing of Boolean functions. This is exactly the problem. So you're given a function f from f2 to the n to f2, and the goal is of a tester will be to query f in few locations and if f is linear, then you want to accept. If f is far from linear, or say epsilon far from linear, then reject. Okay, with some probability, with probability say epsilon naught, which is greater than 0. So say this is the task of linearity testing of Boolean functions. Given oracle access, you want to accept the linear function, and if the function is far from linear, then you want to reject with some noticeable probability. And when I say epsilon far, I mean so for instance, the distance between two functions f and g is the probability that when you take a uniform sample from the domain, f and g differ on that point. Okay, so this is from samples coming from the uniform distribution. What's the probability that f differs from g? That's the distance between f and g. And so f is epsilon far from linear. I mean that epsilon f is the distance of f from every linear function is at least epsilon. Okay, so this is the problem of linearity testing, and this was this problem addressed in fact the seminal work of Blum, Luby, and Rubenfeld, and they show that in fact that you can do this. There is a very simple tester which achieves this task. So what they said was just set sample x and y from f2 to the n independently, uniformly, and check if f of x plus f of y is f of x plus y. Okay. Think of this very simple 3-query test. If f is linear, this test will pass with probability 1, and if f is far from linear, in fact, they show that this test will fail with some noticeable probability. And this tested in fact implies that the Hadamard code is locally testable. Okay, so this is a very well studied problem. Testing the Hadamard code is exactly testing for linearity under the, yeah? You have a question?
Just remind the intuition. The test says that if you pass the test with high probability, that there is one Fourier coefficient which is
Large.
large, right?
Yeah.
That's it.
And that's it. Yeah. So you can this test the acceptance probability of the test you can cast in the language of the Fourier in terms of the Fourier expansion of f, and this being large will exactly translate to some Fourier coefficient being large, and hence f will correlate with some linear function well. Okay, so that's one proof of this result. Okay, anyway, so this test works, and we know the Hadamard code is testable. Okay, so that's great. So how about other codes? Okay, so let's take some general linear code. Okay, so say G is the generator matrix of some linear code. Okay, so we have C, again some subset of f2 to the n, and you'll have this will be say the code is a dimension little n, so this is a little n by capital N matrix. It will have capital N many columns. Okay, so there are n columns. So let this set of these xi's I between 1 and n, let's call this set S. Okay, so S is some subset of f2 to the n. In the Hadamard code, the set S corresponded to all of f2 to the n. A general linear code, you'll have some set S, we'll let the columns be the set S, and there will be some subset of f2 to the n. Okay, so let's take such a linear code. So again, so what are the code words of this code? Okay, so the encoding of a message is again going to be m times x1, so times m up to m times xn. Yeah. Okay, so the code, so this is again looking like a linear function, but a linear function not evaluated in the entire domain, the linear function evaluated on some subset of the domain. Okay, so the code words are the truth tables of the linear functions evaluated on S. We are not looking at the entire domain, on a restricted domain. And a received word you might see out here. This is capital N. This received word is basically some function on S. Okay, so in general, in arbitrary code, you can view it as in this linearity language, where the code words are linear functions on S, the received words are some functions on S. And now deciding if this code is testable or not is asking, is there a tester which will query of some function defined on S and decide is this function linear when restricted to the set S. Okay. Earlier we were talking about restricted linear with respect to the entire domain, and hence the notion of distance was the uniform distance. Let's define a new distribution now. So let mu be the uniform distribution on S. Okay. So if mu is the uniform distribution on S, what now we want to do is the following. The tester must query R in few locations, and if R is linear, then you want to accept. Okay, but if R is far, but now the far we'll do it is in mu distance, then you want to reject with some probability. Okay, so I have translated the question from testing linearity of this code, testing closest to the code, to testing linearity over a general distribution. Okay, so what do I mean by far in this mu distance? Again, the definition is very intuitive. So I call the mu distance of two functions f and g to be the probability that when you sample x from mu, that f of x is not equal to gx. Okay, so now we've got down to the problem of linearity testing in this new language. Okay, so let's talk about linearity testing under general distributions. Okay, so one possible goal was again, if f linear, then accept. If f is far from linear in the mu distance, then reject. So there's one problem with this definition, at least in the setting as we looked at it. So linearity testing under general distributions with this notion was in fact studied before, and Halevi and Kushelowitz, they gave a very simple 3-query test which shows that you can test linearity under all distributions, okay, in particular under this distribution. They gave us simple 3-query test which works even here. Okay. So let me tell you what the catch with this definition as is. Okay, so suppose you have f2 to the n and you have the set S out here, okay, and say I have a function which is purely linear out here on this part, okay, my distribution mu is uniform on S, okay, and I have a function which is random outside, okay, I have a purely linear function here, a random function outside, and I want my tester to accept such functions, right? My distribution mu was uniform on S, I care only about mu, so I should not care what the function looks like outside, okay. So, and even for the coding theory interpretation, your tester is going to make queries only to the function evaluated on S. It doesn't even get access to the function evaluated elsewhere. Okay, so it's very important that the queries come from the set S. In fact, the Halevi-Kushelowitz tester ended up rejecting such functions. It wanted the overall function, the global function, to be linear. This was a tester which worked, which only accepted purely linear functions and rejected functions which were far from linear in mu distance. Yes, but so this is not good enough for us. And let me give a slightly stronger notion of testing linearity which will solve this problem for us. Let me talk about the problem of tolerant linearity testing. So this was a definition which was, this notion of tolerant testing has been around. It was defined by Parnas, Ron, and Rubenfeld. And in the case of testing under general distributions, this is even more natural, and you'd want to consider this. Okay, so under some distribution mu. So the goal is again the same. Let's just strengthen it. So I don't want to say that if f is linear, accept. I want to say if f is close to linear, even then you want to accept with high probability. If f is far from linear, you want to reject. You want to distinguish between far from linear and close to linear and far from linear, not linear and far from linear. Okay, so if f is close to linear in mu distance, then accept, say, with high probability, and if f is far in mu distance, then reject with high probability. Okay? This is a much nicer definition, and if this is the definition you're asking for, this problem you'll never end up accepting such functions, because you never end up rejecting such functions. These functions will be accepted. Okay, and the BLR test in fact works. The BLR tester is in fact a tolerant linearity tester, because it does, if the function is very, very close to linear, it does end up accepting the function. Okay. Yeah.
Even in the non-standard distance, so if it's close on the uniform distribution.
In the uniform distribution.
So it's not clear how to even state it, because x plus y might not be in x.
Exactly. So when I talk about the BLR test, I mean over the uniform distribution. The BLR test with respect to the uniform distribution works tolerantly, but for general distributions, it's not. For some distributions, mu is not even clear that you could have such a tester at all. In fact, I think it's easy to show that there are some distributions which you cannot tolerantly test linearity under. Okay, so given that if f is close, you want to accept, and if f is far, you want to reject. Somehow you're trying to measure the distance of the function to linear functions with respect to a distribution mu, and that's how somehow forcing that each query you make to the distribution must come according to mu. If you're going to use your tester to make queries where the distribution of the queries is not according to mu, and you're using that information, there could be like like some part of the distribution which has a very small, where mu has a very small, small amount of weight on that, you can just corrupt that, and you can, but you still want the tester to accept. So that the tester which is querying parts of the distribution which are not well represented under mu, then that's bad for us. The queries need to come according to mu. So informally or nearly formally, I mean, basically what this is forcing is the queries, each individual query needs to be distributed according to mu. Okay, so that's one sort of requirement any such tester needs to have. Another requirement is that, okay, you need to have queries according to mu, but these queries need to form linear relations among themselves. Otherwise, how do you test linearity without having linear relations? Okay, so the queries need to come in some sort of correlated fashion, need to be correlated to form linear relations. These are the two basic requirements. You need to have queries according to mu, the queries need to form linear relations, and there are distributions for which you cannot do this. Like suppose the set S is a very, very small set, small random set. Okay, there's no way of getting few queries according from S and correlating them to form linear relations.
But then, okay, then pretty much any function is going to be approximately linear because
I guess you still want a global linear function that you're close to on that set. So it's a weird definition of that setting. So restricting to the set, you can't tell whether a function is linear or not. You still want to be close to some globally linear function.
okay.
You can tell, but not locally.
You can't tell locally. If you look at the entire set.
Instead of the many queries, it would be the few queries.
But the thing is, the first definition was like legitimate. If you just say that, like, I mean, if you don't necessarily want tolerant ending, but if you really want that, you accept functions that are linear when restricted to the set.
Yeah.
Then that's still like a legitimate question. And in that case, you might not want to make queries that are distributed according to mu.
So the point is that you won't have any small number of queries
Right.
that
Right.
That are linear
Right, right,
combinations.
right,
But even
right.
with this random set, if
Right.
you pick n queries,
Right.
then they'll be linearly
Right.
dependent,
Right.
and
Right.
then there will be some constraints.
Right. Right.
Well, actually, I mean, the problem is easy if it's like a really small, like it's a linearly independent set, right?
Not a linearly independent. I meant take a set of size 2 to the root n. So let's take a set of size, a random set of size 2 to the root n, sitting inside f2 to the n.
But then you can probably just always say yes, right?
No.
No, you cannot.
Because so as long as the set's bigger than n,
I see.
then it'll have linear dependencies.
Right.
The big ones.
But big ones. So that means that you can test, but not efficiently. Not with a constant number of queries.
What kind of access are you assuming? So the tester has full knowledge of the distribution.
See, so right now it's just very information theoretic. I have full knowledge of the distribution. I know everything.
The probability of any point.
I can do. I know everything about the distribution. I have unbounded computational power. Only the number of queries right now I'm trying to restrict the number of queries. With constantly many queries, make this decision. And I agree with you that you don't. This tolerant testing is slightly maybe stronger than what you need. Where at least in this setting, in locally testable code, I just wanted my queries to come from the distribution, not necessarily distributed according to the distribution. But I don't know a separation right now where you might make this might be too strong.
I guess that if the distribution is very far from you can corrupt a lot of points, right? So
Yeah, I agree. The distribution is very far. It will be somewhat. Yeah.
so if it's very close to you, you can probably change it a little bit and still get your linear relations with good probability.
So only what could be that there may be one query which I'll always query this fellow. Okay, and then if I just want to accept things, so then the distribution of the first query is very, very far from you, but it is still a valid tester if I just want to test the code, if I want to accept.
So saying that since the adversary could make that a random value, you
Right.
could simulate such a tester without making that query by just plugging in a random value for that query.
Say basically,
Yeah.
So anyway, if you can tolerantly test under mu, then clearly the underlying code is locally testable. Okay. In the other direction, the connection is not as strong. So I don't know how to say that if a code is locally testable with this strong definition that you only ask to accept things in the code and reject things far from the code, whether this translates exactly to tolerant testing, it's not clear. Tolerant testing of the code will translate to tolerant testing of the underlying distribution. But the exact connection is not quite tight, and I'm not sure. Okay, but if you start with the code, look at the underlying distribution which is uniform over the set, corresponding set S, then tolerant testing under that distribution, if you can do tolerant testing under that distribution, it will translate to a test for the code. Okay, but just testing under the distribution won't translate into a test for the code. You need to be able to tolerantly test. The stronger notion of testing was necessary. I don't know. Yes. Yeah, I'm not sure.
Well, yes, because Halevian Krushchev
Okay.
can do testing for arbitrary distributions, but you can't do tolerant testing for arbitrary distributions. You can only
For distributions, okay, but for codes, it's not. For codes, that's not, that contradiction doesn't hold for codes. It only holds for distributions.
If you queries, then if you're very close, you just won't notice the difference anyways.
So Halevi-Kushilevitz ended up making queries outside the set S.
Yeah, but then the definition of acceptance is different, right?
So
If you translate to a function, yeah,
yeah. So that doesn't even give you an algorithm in the code set.
right. So yeah. So talking about translate, yeah, there's no nice way of translating into a function and talking, translating to a function on the whole domain and then talking about testing there. Anyway, yeah. So now let's study tolerant testing under mu. So all distributions mu we cannot tolerantly test under. So the question is, for what distributions mu can you test tolerantly under? Okay. So we don't know a good classification of this question. I think that's quite very interesting to understand what distributions mu will have this property for which we can do tolerant testing of linearity. Yeah, but anyways, these two criteria roughly need to be satisfied. The queries need to be distributed according to mu or to a distribution very close to mu, and the queries need to satisfy linear relations. Okay. So we don't fully classify how we can tolerantly test under mu, but we give a sufficient criterion for being able to test under mu. Okay. So and the criterions are following. So I say that the distribution mu is k uniformly correlatable. Okay, if the following holds. If there exists the following joint distribution, x1 up to xk. Okay, I have a joint distribution of k random variables. Each xi is, the distribution of each xi is according to mu. Okay, and the sum of the xi's, the distribution of this is the uniform distribution. Okay, so I start with an arbitrary distribution mu. I call it k uniformly correlatable, which means I can take k samples and correlate to the uniform distribution. That's what I mean. If there exists this joint distribution of k random variables, each one individually distributed according to mu, and the sum is uniform. Okay, if such a joint distribution exists, then I say mu is k uniformly correlatable. Okay, and the main result, so the theorem says, if mu is k uniformly correlatable, then we can test linearity. Then linearity is tolerantly testable under mu in order k queries. Okay, so the need for being able to correlate, getting samples from mu and correlate them nicely anyways was an important condition. And we showed that in fact if we can just correlate to them some way to reach the uniform distribution, then we can tolerantly test linearity under mu. or very close to u. Oh, what has to be exactly what? Uniform?
The sum should be exactly uniform.
Or epsilon close to uniform for very small epsilon, and that won't change much. Okay, so close to u also, very, very close to u. See.
Sorry, the sum is just uniform on a subspace?
So I meant uniform, u sub n was uniform on all of f2 to the n, but subspace might have worked, but never. Not uniform on a subspace, because the subspace could be 0, just the element 0, and just being able to correlate to form some linear relation was not enough. So un is uniform on all of f2 to the n.
But you can parameterize it by the definition by a subspace, right?
Pardon?
You can parameterize it by a definition on the subspace or something like that. Let us say you get a uniform point from the subspace.
If mu was supported in a subspace and I could get uniform on that subspace, then I can still test linearity. If mu is supported everywhere and I get uniform on a very small subspace, then I don't know anything.
Right, right.
But you get 0, it's also good for you, right?
I cannot say. It's good that these two conditions are satisfied and it's necessary, but I can't say it's sufficient. I'm not able to say that if you get 0, then I don't know how to prove that.
I guess I was just thinking like one natural case where you should be able to tolerantly test is when mu itself is uniform on a subspace.
Oh, right. So if,
It's very easy,
yeah,
but it's
that's.
not covered by this.
I agree. This is a sufficient condition. There could be, yeah. So there are, yeah.
If mu is supported on a subspace,
Yeah.
you'll never have this.
I'll never have this property, and so I'm never addressing these questions at all. So let's assume first, for now, that at least mu is supported everywhere. Otherwise, we can always restrict to the subspace and then work in that subspace from then onwards and forget n. So let's assume that mu is not supported, not restricted to any subspace, and then this is the condition. But this is not. We can come up with distributions not satisfied. So this is definitely not if and only if. Okay. Okay, so this is so if you can correlate to be uniform in the entire subspace, then we show that this is testable, and so that's the main result. But now using this, we can also show that many interesting classes of distributions satisfy this property. So the question is, what distributions can you correlate to reach the uniform distribution very easily? And there's some very nice examples of such distributions. Okay, so for instance, the p-biased distribution. Okay, suppose we don't have the uniform distribution. We have a 1 with probability p and 0 with probability 1 minus p. So we see 1 with probability p, 0 with probability 1 minus p. Okay, let's look at this distribution for where p is some constant, say 1/4 or 1/10. Okay. So a priori it's not clear how to tolerantly test linearity under with this distribution at all, and whatever tests we have fail. But using this, but a p-biased distribution, in fact, we can correlate to get to the uniform distribution. You can take samples from them, correlate them cleverly to reach the uniform distribution, and hence we know how to test. So now we can test linearity under the p-biased distribution.
K is going to be about 1 in p, or
1 over p, yeah, if p is small, yeah.
so then it's just unique correlation, or it's just sum? The sum is going to.
You need correlation, because say if p is 1/4, then we take few random samples from p, then it won't become half. It won't be uniform. It will be some other q-biased, and still, and that distribution will still be very, very far from uniform. So you need to cleverly correlate it. So to get to the uniform distribution for a constant k. Yeah, if you take lot like n many samples, even log many, probably you reach very close to the uniform distribution. That's good enough. But if you want to take constantly many samples, so if say p is a constant and you want constantly many samples to reach the uniform distribution, then you would need some clever correlation. So maybe I won't. So you can just hack out by hand. It's not hard to see how you would do. Okay, sure. Okay, so say. Okay, good.
If you remember it.
So let me try. Okay, so say it's okay, good. So let's say we want to have a p-biased distribution and p is very small, say 1/10 or something. Okay, I'll show how to take 2 copies of 2 p-biased samples and get them closer to half. Okay, get it much closer to half. And so let's see how. So let's just understand, if you take two p-biased variables, how close can you get to half? Let's just understand how it works. Okay, so just take 2 p-biased bits. Good. So you have 2 p-biased bits. So say n is 1. So you have x1 and x2. Okay, so what values can x1, x2 take? It could be 0, 0, 0, 1, 1, 0, or 1, 1. Okay, so to understand. So I want to tell you what should be the probability. So it's a joint distribution I want to come up with. So I want to tell you what is the probability of 0, 0, 0, 1, 1, 0, and 1, 1.
So I think you want to eliminate 1, 1, right?
Maybe you want to eliminate 1, 1, but you might overshoot and go beyond half. So if I want to eventually reach exactly half.
Oh, okay.
So I want to if I eliminate 1, 1, then I'll come as close. I mean, so if
it were a quarter, then you just eliminate.
exactly, if it was a quarter, I would just eliminate 1, 1, I think, and that would work. So say the probability of 0, 0 is A, probability of this is B, C, and D. I know that the probability of x1 being 1 should be P. Okay, so I know that C plus D should equal P. That's one constraint I have. And x2 has to be 1, so I know that B plus D.
Then you can make B equal to C just because.
P. Oh, and by symmetry, I guess, okay, yeah, sure, B can be equal to C. Yeah, might as well.
Oh, so you lost an equation, sorry.
But maybe that won't hurt. Okay, so B plus, at least in this case, so B plus D is P. And I know that A plus B plus C plus D is 1. So A plus C is 1 minus P.
You want to make A plus D as close to 2B as possible.
And I want to make
A plus D
A
as
plus D,
close
so
to 2B as possible.
so I want the probability of 1 to grow, so B to be as large as possible, right?
Well, up to a half.
Is less than half?
Up to a half. So if P was very small, so basically I want B to equal half or as close to half as possible.
So if P is below a quarter, you can just do Russell and just make it never have 1, 1.
Exactly. If P was below a quarter, you can get it up to you can just eliminate the D and get it as you can double it. Okay. But now once suppose P something between 1/4 and a half, then
You want A
you
plus D to equal 2B.
exactly you would want A plus D equal to 2B. You would set B equal to half, and you solve a linear system, and you manage to make it reach. Okay, so that's it. Okay, so good. That was a sketch of proof for. Okay, so the p-bias distribution is one example of a distribution which you could correlate to make uniform, and hence use this criterion and give the test. So another interesting class of distributions is symmetric. So this was a p-bias distribution where each bit came with p. What if you have a distribution like, okay, so the symmetric distributions supported on words of weight gamma and 1 minus. This is another class of distribution. So suppose I don't want the p-bias distribution. What if I wanted the uniform distribution on all words of weight exactly n over 4? Okay, so that's one distribution. Or in particular, if the weight of my on a particular element depended only on the number of ones in it. So that's those distributions are the symmetric distributions, and symmetric distributions which are supported on in words where the number of ones is reasonable, not too close to 0 or not too close to n. Then those distributions can also be correlated. But don't ask me to do the correlation now. This is much trickier.
So then it's just, well, so if you want to like move it to support n over words of weight n over 2 approximately, then you just pick the intersection size pretty much like you did.
It's just a bit more hacky to get it done, but this is not so hard. I mean, this is again you can just do by hand. There's nothing very clever. Once you know that you want to correlate this to uniform, you can just do it.
You can just sort of think of each, pick some of the locations in each of your samples to be uniform, and then fix the rest in that sample, and then you divide the locations that are uniform among your samples and the sum.
Well, you want to pick the size of the intersection according to some distribution, and
What do you mean
then
by intersection?
the rest is determined.
What do you mean by intersection?
So we say that it's just exactly gamma n ones. Okay, is the distribution. So each one's going to have a set of gamma n ones.
Right.
All that really matters is how big the intersection of those two sets is.
If you have two.
You have two of them.
Right.
So you just have to pick, if you pick it, if gamma is very small, you pick the intersection size to be 0,
Right.
and you double gamma. Once gamma gets big, you try to make it some binomial binomial distribution.
roughly that, yeah. You grow balls and you make it, you play around with it. There's nothing very too interesting here. Okay. So there's another class of distributions which is maybe the most interesting. I don't know. So this is the set of unbiased distributions, distributions which have small Fourier coefficients. Okay, so if mu is such that, if you given the distribution, you can look at the Fourier transform of the distribution. So look at the value in all the characters. So if for all characters, all sets S which are the non-trivial, if the expected value of chi sub S of x, where x comes from mu, if this quantity is small, and small is going to be something like 2 to the epsilon n. Okay, 2 to the minus, sorry. Okay, if your distribution satisfies this property, then also mu is uniformly correlatable.
This time you just take independent.
This time you just take independent copies. If your distribution has such a property that all the Fourier quotients are very, very small, then just independent copies of f. If you just take enough independent copies, a large constant like say 10 over epsilon independent copies, then you'll be super close to the uniform distribution. Okay? So what is this so one nice example of an unbiased distribution is the following. So a random set. Oh, sorry?
Can you get it to be exactly uniform? Can you
Super close, like 2 to the minus n close to uniform.
Let's if you choose them independently.
We choose them.
Then correlate two such copies to make it exactly uniform?
I don't know. I'm not sure. I'm not sure how to get the error down to 0. Some linear equations you write. I don't know how to get it exactly 0. But this could be like minus 2 to the minus 10 and close to uniform, like super close, but I don't know how to make it 0. Okay, so let me go to that board. Okay, so an example. This one.
So probably not because the space of correlated distributions like that.
Okay, so these unbiased distributions. The unbiased distribution you can correlate to the uniform distribution, and in particular, so if S, so one example of an unbiased distribution is let S be a subset of f2 to the n, and this is a random set, and size of S is like something like 2 to the gamma n for small constant gamma. So a random set of size 2 to the 0.1 n. If you look at the uniform distribution on that and look at the expected bias of the Fourier coefficients, then it's very, very small. Okay, so such a set satisfies that criterion, and such a set, so this random set actually corresponds. So if you look at the code interpretation of this, this translates to a random code. A sparse random code. Okay, so set of size 2 to the gamma n sitting inside 2 to the n translates to, so this will be like n bits mapping, so a code, so this will translate to a random code mapping n bits to n bits. This capital N is going to be 2 to the gamma n. Okay, so so the length of the code is 2 to the gamma n, and this code is subset of f2 to the n. Okay, so this code is going to have roughly n to the 1 over gamma code words.
See inside f2 to the capital.
No, see the subset. Oh yes.
Okay, so we look at a code C subset of, if I take a random code inside f2 to the capital N, which has n to the t, so some polynomial number of code words, and here t will be something like 1 over gamma. So take a random code with polynomially many code words. Then the corresponding set will have small bias, and such a code is going to be hence locally testable. So basically sparse random linear codes are locally testable.
So do you need that? You need that larger size for S to get anything to work?
Yeah. So again, if the size S, if the code was not sparse, so not polynomially many code words, which would translate to the set S being smaller than 2 to the epsilon n. If the set was going to be like 2 to the root n, then we cannot form linear relations, and there's no hope of testing it because there probably would be no linear relations of width smaller than root n. So there's in such a case there's no hope of testing at all.
So it is for any code or random code. So this method will not
So an
work.
unbiased code. So in particular an unbiased code. So unbiased codes, unbiased sparse codes. And by unbiased codes I mean that the weight of every code word, the Hamming weight is basically half plus between half minus n to the same, some constant n to the minus gamma, say. Okay, so the weight is each code word is roughly balanced ones and minus ones. If you have an unbiased code, then it's locally decodable, locally testable. But the sparse was also important. Where the number of the codes are only polynomially, there are only polynomially many code words in the code. Okay, so this for this particular setting of unbiased codes, this was actually shown before. So Kaufman and Sudan, they showed this result for codes over F2, and Vidad showed this for codes over larger characteristic, over FP, that such codes have the property of being locally testable. But the proof was through very, very different route, much more coding theory using Krautchuk polynomials, etc. This is a completely different approach to understanding the same question and getting the same answer. Okay, so they show that unbiased sparse codes are locally testable codes. Okay.
Didn't they remove the unbiased condition for F2? Kaufman and Sudan?
They could show Kaufman and Sudan could even show this for codes which have very, very large distance, which is a slightly more general property than being unbiased, with codes having distance nearly half. Okay. Another interesting class of codes which have this unbiased property is dual BCH codes. And for these codes also, then it was known separately that they were locally testable through separate means, but this proof generalizes and shows the local testability of dual BCH codes too. And so in the rest of the talk, I'll prove this criterion, that if you have satisfied the sufficient criterion of being k uniformly correlatable, then you're testable. I'll show this. It's not that hard. And then we'll just focus on this particular case of unbiased codes or unbiased distributions and show that in fact something much stronger is true for these distributions. You can test with much higher, you can test all the way. You don't have to just distinguish between near the code and far from the code, but you can actually estimate the distance of the received word from the code up to whatever accuracy you want to.
Do you want a break or do you want to keep going?
I'm okay both ways. So I can keep going, but if we can take a break just for 5 minutes anyways.
Sounds like it's a stopping.
This is a stopping point, definitely. This is,
So why don't we take just a small break?
yeah. Yeah.
Should I have a short analysis or can you just need that to show that?
Yeah, so I'll go on. I'll prove this sufficient criterion that if the distribution has this property of being k uniformly correlatable, then you can tolerantly test under it. Okay, so I'll give 2 tests for this. And if both tests pass, then we'll certify that the function is close to being linear. Okay, so the test 1. Okay, so we can sample from mu and correlate them to reach the uniform distribution. We'll use this property, these correlations which we get, to design our test. Okay, so test 1 is going to work like the following. So it's going to be, first let's sample x and y from the uniform distribution. Okay, and let z equal to x plus y. Okay. So we don't want to evaluate the function f at these points at all, because we don't want to deduce anything of worth from the uniform distribution. Okay, but what we can do is we can reach the uniform distribution given samples from the mu distribution. So let's do that. Okay, so maybe, okay, so actually let me set up some notation to make things simpler. So let me call the distribution mu to the k to be this joint distribution, x1 up to xk. Okay, so that's the mu to the k distribution. I'll call mu to the k conditioned on the sum of xi being x to be this distribution. Okay, so I'll be using these words. Okay, so let's sample x, y, and z coming from the uniform distribution so that the sum is 0. And now let's sample. So let's, instead of evaluating at x, y, and z, let's evaluate on these. So let's sample x1 to xk now, coming from mu to the k, conditioned on the sum of the xi's being x. Let's sample y1 to yk from mu to the k, conditioned on the sum of the yi is equal to y, and sample z1 to zk from mu to the k, condition summation zi.
So these conditional distributions aren't easy to sample.
They aren't easy to sample. So this
This is a thought experiment, right?
This is not even a thought experiment. When I'm talking about these testers, I didn't say that they were time efficient at all.
Oh, okay.
I'm just talking about the query complexity. The time to do this sampling, that I have unbounded computational power. I can understand these distributions fully as a tester. I only want to make few queries into the function to do the testing. That's the only thing. So this sampling I can do.
But in some of the examples you were talking about,
Maybe you can do better. For some nice distributions, maybe you can do things more cleverly. Maybe the p-bias distribution, you can do things cleverly. Other distributions, maybe.
there's no need to think about sampling x and y and then fitting x1 to xk. Oh, I guess for z you're doing
Yeah.
Is it the case for all the p-bias distribution?
The back, I think with the p-bias, the back sampling should be easy, but like for the random case, unbiased case, not at all. It might just be completely.
But for dual BCH,
So a special case, I talked about dual BCH codes being unbiased codes, and for these codes, the very structured codes which are very unbiased, and here the back sampling, this sampling process is easy. So with the dual BCH codes, you not only get local testers, you also get efficient local testers for these codes. Okay, so anyways, let's sample these codes, and now the test is what you would want it to be. So check if sum of f of xi plus sum of f of yi. Okay, so that's the test we do. So notice that each time you're evaluating f at a value, it came from the mu distribution. Okay, and you made the test, and you got a linear relation amongst the xi's, yi's, and zi's by the way you sampled. Okay, so this was very nice, and this is also very, very reminiscent right now of the BLR test, the BLR linearity test, where you sampled x, y from the uniform distribution and checked if fx plus f of y is in z. Okay, so this is, so in spirit, this is the BLR test. Okay, so let's understand this test better. So what just happened? Okay, So it's a BLR test applied not to f, but to to the sum of f at lots of values. Okay, so let me define a new function h, which will help us understand this test better. So let's define h of x to be the following function. So it's going to be a probabilistic function. I will define, in fact, h of x to be sum of f of xi, where the xi's come from mu k condition on the sum of the xi equal to x. Okay? So this is a probabilistic function. To evaluate the function h at a point x, I'll sample the xi's from this distribution. I'll evaluate f in this fashion, and this is a probabilistic function I can define. Okay?
But on the other hand, it can't be too probabilistic and still obey that test.
If this test, okay, exactly, yeah, good. Okay, so if this, so now what I've done is this test that I have applied is exactly applying the BLR test on the function h. And if this test passes with high probability, it must be by the BLR analysis, and the BLR analysis works even for probabilistic functions. It didn't have to be deterministic at all. So if this test passes with high probability, we know that the function h is close to a linear function. Okay, so if test 1 passes with high probability, then h is close to a linear function g, but this is under the uniform distribution. The BLR test only worked over the uniform distribution. So this test passing with high probability is exactly the same as saying this new function h is close to a some linear function g under the uniform distribution. Okay, this is not quite what we wanted, but this is what we get out of test 1. We can start with f, define a new function h, and know that it is close to linear in general over the uniform distribution. Okay, but what we wanted was to show that the original function f is close to some linear function g under the mu distribution. So test 2 will help us do exactly that. So here's test 2. Okay, so the way test 2 is going to be is the following. So sample x from the mu distribution, and now sample y and z coming from the uniform distribution, but correlated such that x is y plus z. And this we can do. So just sample y uniformly from the uniform distribution and let z be x plus y. So then individually each of y and z will be from the uniform distribution, and the sum will be x, which is from the mu distribution. Okay, and now the test is going to be again, so but now y and z are from the uniform distribution, so you cannot evaluate anything on the uniform distribution. So let's, as before, sample y1 to yk, coming from mu k condition on the sum being y, and z1 to zk coming from mu k condition on the sum of the zi's being z. Okay, and just check if f of x is equal to sum of f of yi plus sum of f of zi.
We can say that's equal to h of y plus h of z,
which is going to be g of y plus g of z,
yeah.
which is g of x. So that was, so why, suppose this test passes with high probability. What does this mean? Because that's the test. Okay, but this test, okay, so if this test passes with high probability, so now summation f of y is just h of y, and this is just h of z. Okay, so then I know if this passes with high probability, then I know that f of x is almost always h, which is h of y plus h of z. Okay, but if test 1 had already passed with high probability, then h is basically the linear function g. Okay, so this is g of y plus g of z. Okay, but g is linear, so this is g of y plus z, which is g of x. Okay, so now x was sampled from the mu distribution, and we get that f must equal g when x is sampled from the mu distribution. That's it. Okay, so if test 1 and test 2 both pass with high probability, that finishes. That then must have been that the function f was close to some linear function g under the mu distribution. Okay, so that's the full proof. Okay, so just so just summarizing what happened. So what we did was we took f. So f was on mu. The first step was we extend f to a function h, which we care about on all of the uniform distribution. Okay, so we used f to first create a function on the full space, test linearity of h under un, and then so if h was linear under the uniform distribution, then you were going to test if that is the case, you want then also test that f is close to h itself under the mu distribution. Okay, so we took a function, extended to the entire domain, checked that that was linear, and then if that's linear, then check if the original function in fact agrees with that the extended function on the domain you started out with. Okay, so that's the.
So you haven't exactly said that this always works if f is linear on mu.
If f is linear on mu, if f is linear, this test will pass. So if this test passed, I told you that f must be close to linear.
Oh yes, if the test passes, it must be close to linear.
The other direction, the other direction is clear because each time I made a test, the samples came from mu. So if f was close to a linear function g on mu, each time I made this test, I can replace f with g, and the test would just pass. Each time I sample x from mu, f of x is going to be almost certainly equal to g of x, and so both the tests would pass because each time I evaluated f, each test I made, the queries individually the queries were according to mu.
So that's a minor thing, but like the zi's are not the sum. Oh, I see. Yes, it will pass. Okay. Yeah. Right.
So this is almost a reduction between distributions. You know, if you replace the uniform distribution with some other distribution that you know how to test, and you can correlate copies of mu to get, say, some distribution sigma that you know how to test.
Yeah.
The one thing that's missing is this test 2.
Yeah.
But you could probably formalize what a test 2 is too, right?
So again, really what the problem could be. So let's hope that this would work always. Whenever you can reduce to a distribution that you could test, then maybe the original distribution is also testable. But look at the distribution which is just supported on the point 0. So the distribution is 1 on 0 and 0 everywhere else. So that distribution is clearly testable.
Right.
But I don't know how to say that if you can, when reducing to that distribution is just saying being able to correlate copies to sum to 0.
But you have to be able to do the second part.
Yeah, so the second part doesn't quite work out. I'm somehow using the uniformness heavily. I don't know how.
In y and z, the fact that y plus mu sample.
Oh yeah, good. I think that's the crucial step. Yeah, the crucial step was being able to take 2 samples from the new distribution and correlate them to get to that's the place where we are using.
So it seems like we have to be able to get. So it seems like to get the reduction or equivalence, somehow if you could.
Both ways get correlations. Yeah. So take mu correlate copies to get the some other distribution, and then correlate copies with other distribution.
And then you say like the testing is equivalent.
looks like it, right? Maybe that will just work. I mean, you just make that test 2 and that would just prove that, yeah, if 2 distributions can view and reach both ways, then yeah, that might be right. I don't know. Yeah.
So all you care about is that in sampling these strings is that each yi is marginally distributed according to mu.
Yeah.
That's it.
Yeah.
You don't say how to. You don't. And you said you're not getting into how to correlate these strings.
So I know that the correlation exists. That there was a condition. I started with a distribution for which I knew that it was correlatable to get to the uniform distribution. These correlations exist. And I'm saying just take these correlations. I mean, I know they exist, so the time complexity I don't know about. Yeah.
Are there in these testing problems? I guess in the previous works were the testing algorithms computationally efficient?
They weren't. Again, yeah.
We don't know whether.
For random codes, I think for random codes, it's possible. It should be quite easy to show that you cannot do this efficiently.
Just too many of them.
Yeah. You just to form a linear relation. I mean, how do you know what samples to take to form a linear relation? You probably search over all subsets of size k before you even start finding relations. Yeah.
It's constant to go fine, right?
But the size of the code is constant in what? The size, the length of the code is 2 to the n. You have to run in time. So efficient is depending on what. So I think if the code is sparse and the length of the code is too much, then I think the notion of efficiency you're going to use is log of the size of the length of the code. And dual BCH codes you can make in run in time polylog the length of the code. But you would have to run in polynomial in the length of the code for all these things to work out, which is polynomial in 2 to the n. So depending on what you mean by efficient.
And only the size of the code can be done?
That can be done. Just by trying all that probably can be done, yeah. You look at, to query a particular point, you look at what k tuples sum to it and then uniformly sample amongst one of these.
Not to mention the code has polynomially many code points. So
Oh yeah, but
that's not the right question.
you can just say, take, yeah. Okay, so good. So this completely finishes this part of it. Okay, good. So we extended f to h, we tested linearity of h, and then we tested if f was close to h under mu. Okay. So it's quite interesting. I should mention this. It's quite interesting to understand. So 2 questions. First of all, what distributions mu have this property of being uniformly correlatable, and in general, like what codes are testable. So maybe this is just a sufficient criterion. Maybe you can have a tighter criterion which fully characterizes it, but we don't know at all. And we even made a conjecture that all distributions with sufficient entropy. So you need the distribution to have sufficient entropy to have any hope of being able to uniformly correlate it. And we thought maybe all distributions have this property, but we're having a really hard time coming up with distributions which didn't have this property. So Elie Ben Sasson and his student Michael Witheman, they came up with codes, sparse codes. Any nice conjecture we came up with, they were able to come up with a code which met all those but was not testable. So we don't understand it at all really. So what makes distributions correlatable or nearly correlatable, or what makes codes testable?
Do you have examples of codes that are testable and are not correlatable?
I'm sure. So not correlatable, yeah, that is quite easy to construct because these correlatable codes need to be very, very sparse codes. You can come up with much denser codes which are testable, but there's no hope of correlating. So one example like which Ryan just mentioned, like suppose the message is x1, x2 up to xn, and the code word is just a parity of every pair of things. So this we can show that's testable, but there's no hope of correlating. Okay. So this was local testing of codes, and so the problem was you want to make few queries and decide is the received word close to the code or far from the code. Okay, but so you can ask for a much stronger notion of testing. So let's see some other notions of testing. Okay, one is dealing with high error. So here you wanted the tester to accept only received word which is very, very close to the code and reject everything which was far away. Okay? But can you one task you might want to ask is, can you distinguish between the received word being arbitrary, a random string, versus having some correlation with the code word? Okay, so one thing you could ask for is, if the distance between the received word and the code, this is less than half minus epsilon, then you want to accept. Otherwise, reject. So if it's in particular, if the distance between R and the code, and if it's very close to half, okay, or half minus a much smaller constant, then you want to reject. Okay. So this is testing in the very, very high regime. When you want to test, is the receiver at all correlated with your code word? Okay, this could be one notion. Or something even stronger is distance estimation. You want to actually by making few queries to the code, to the received word, you want to actually be able to estimate the distance of that received word to the closest code word. Okay, so what that could mean is the following. So let's take any two constants, epsilon 1 and epsilon 2, between 0 and a half. And you might want that if the distance of the received word to the code, this is smaller than epsilon 1, then you want to accept. And if the distance between the received word and the code is greater than epsilon 2, you want to reject. So this is really the strongest notion you can ask for. By making constantly many queries, you want to actually, up to any small constant, be able to estimate what the distance is to the code. Okay. So can these tests ever hope to do something like this? So the reason is no. Suppose you want to have the stronger goal of being able to estimate the distance. What might happen is you can start with a function. You might be able to start with the function f, which is say 1/4 close to linear on mu. Okay? But once you correlate samples and using these funny correlations, you create this function h. You might suddenly be as far from linear as possible. You might look random. This new function h is made by correlating copies from f in a very crazy way. We have no guarantee over it. We just know that those correlations exist. Okay, so functions which are somewhat close to linear might be the distance to linear might be arbitrarily ruined by these correlations. So translating testing from f to translating to that of h will not work when you're trying to really understand the distance with such fine granularity. These tests are not going to do it. Okay, so in general, for distributions, we don't know how to get such strong properties. But for unbiased distributions, those distributions which had very, very small Fourier transfer, the Fourier quotients are very small, or for random codes or dual BCH codes, all those codes or those distributions whose Fourier bias was very small, for those distributions actually we can even get distance estimation. Okay, so sparse random codes or dual BCH codes, with constantly many queries we can estimate the distance to the code word. We can even locally list decode these codes. Okay? And the special property that these codes have, which is going to allow for these properties, is that to create those correlations, we didn't have to just independent samples from the distribution led to the uniform distribution. We didn't have to create complicated correlations to reach to the uniform distribution. Independent samples got us to the uniform distribution. Okay? So that's the property which will enable us to get distance estimation as well as local list decoding, etc. Okay? So somehow we're going to take what's really happening is we're taking these questions about distributions and transferring them to questions about the uniform distribution somehow. Okay? And all these properties we know for the uniform distribution. For the Hadamard code or for functions, we are able to, we actually can do distance estimation. The Goldrack-Levin algorithm gives us local list decoding. And the Goldrack-Levin algorithm combined with the BLR linearity test gives us distance estimation too. Okay, so all this is something we know from the uniform distribution. Okay, so somehow we want to show that for distributions with small bias or for random codes, whatever we can do for the Hadamard code or whatever we can do for the uniform distribution, we can basically do for these unbiased codes too. Okay, so.
Sorry, your sufficient criteria just that the mu changes to be the independent copies of mu?
Yeah. Yeah. whenever you can take independent copies of mu to get to the uniform distribution, and that's exactly the same condition as saying that all the Fourier coefficients are like 2 to the minus epsilon n small. Then all those distributions and the corresponding codes have this property. Okay, so what am I trying to say? So in coding language or I don't know. Okay. Anyway, so for all, let me just say this in coding language because the application is nicest there. So for all linear codes, and even sparse. Okay, so for all sparse linear codes C that are unbiased. So C is again a subset of f2 to the n, okay, that are unbiased. So when I mean that the weight of any code word is something like between half plus minus n to the minus gamma for some constant gamma. Okay. For any such code, C is the strongly locally testable, let me call it, which is all these things. Because you can tell if it's random or it's correlated with the code, distinguish between, basically be able to, given a received word, be able to estimate the distance of the receiver from the code. So it's strongly locally testable and even locally list decodable. And all this in basically poly 1 over epsilon queries. And the epsilon is going to be the min of epsilon 1 or epsilon 2. It's basically polynomial number of queries, but the polynomial is the.
This is epsilon 1.
If epsilon 2 is super close to half, also this poly in epsilon 1, epsilon 2, 1, half minus epsilon 1.
Yeah.
Some poly. Then also 1 over epsilon 2 minus epsilon 1 will also show up. So all the differences you take possible and poly in that number of queries. Yeah. Okay. So then C has these very, very strong properties. So that's the result. Okay. So in particular, and sparse random codes have this. So you can do this for sparse random codes, and you can do this even for dual BCH codes. These are probably the most natural classes of codes which have this property. Okay. And so what's the, so how are we going to do this? So okay, so almost the same way as before.
So this code is not sparse. So how sparse does it need to be?
Polynomially many code words. If this code was not sparse, then this criterion of the weight translating into small Fourier coefficients will not happen. The sparsity of the codes coupled with this weight being small translates into the Fourier transform of the resulting distribution having a small bias.
Does suffice for the Fourier coefficient to be small?
The Fourier coefficient being small suffices, but that's equivalent to the corresponding code being sparse and small weight. A non-sparse code will not have small Fourier coefficients. That's as small, 2 to the minus epsilon n. It will never get that small. Okay. So the outline of the proof is again going to be the. Okay, we'll again. So this is the language of codes, but the same thing holds in the distribution language too. And so you're given so being locally testable of the code is same as you're given a function f and you want to find the distance, estimate the distance to the nearest linear function. Or locally list decoding is find all the linear functions which correlate with the code. Okay. So the proof outline is going to be just like before. So we'll extend f on mu. So mu was a distribution with small Fourier coefficients. We'll extend mu f, which is on mu, to h on the uniform distribution. Okay, and this will be just as before. Okay, this is the definition of how we reach from f to h will be exactly as before. Okay, but we'll use but what was crucial for us was that independent, I'll show this also, independent copies of mu, few independent copies. If you take some constantly many independent copies of mu, you get super close to the uniform distribution, like 2 to the minus 10n close to the uniform distribution. So really, really close. So once we have this property that few independent copies are super close to the uniform distribution, what we'll be able to show is that when you extend f, which was defined on mu, to this function h, then the distance of f from linear functions is going to be strongly tied, strongly correlated to the distance of h from the linear functions on un. Okay, so knowing the distance of the mu distance of f from the set of linear functions, if we know this value, I mean this determines the uniform distance of h from the set of linear functions. It's not equals, it determines. I mean. So this is
because so it's going to be just the closeness is sort of the maximum Fourier coefficient.
Yeah.
Right, and then the point is that the Fourier coefficients are just going to be raised to some power when you take the number of copies power, something like that.
Basically. So I'll prove this in more detail. But this is just a Fourier calculation which needs to be done at this point once you have this property. So this is not very hard to see, but it's a short proof, but I'll show this. So knowing the value of exactly, so understanding how, and forget this is even with any respect to take any particular linear function g. Okay? Take any fixed linear function g. If you know the distance of h from g under the uniform distribution, this will tell you the mu distance of f from g. Okay? Or in particular, so if this quantity is, say, I think this is 1 minus epsilon over 2, then this is going to be 1 minus epsilon to the k over 2. This is the exact translation from one to the other. Okay, so
Just for any g or for linear g?
For linear g, take any linear function g. Then the distance, if you know the mu distance of f, if you know the uniform distance of h from g, then you can know what the mu distance of f from g is. Okay, so but this problem is something we can compute, because over the uniform distribution we know how to, and we know how we can use all the Goldrake-Levin algorithm, BLR, etc., to be able to do this task over the uniform distribution. Okay? So another question is, which is just obvious, but let me just say it. So we were given this problem over f, we've constructed this function h, but we were given oracle access to f. But everything we've talked about, it's clear that given oracle access to f, we can simulate oracle access to h. Right? Because to sample from h, we just have to back sample from this distribution. Okay? So just to know, yeah, so this was point 3, and point 4 was given oracle access to f, we could simulate access to h. Yeah? So now, given these 4 properties, we are done. I don't have to talk. I mean, this implies that for these codes we can do distance estimation, local list decoding, everything. So I just had to show that these properties hold. Given this property 4 was clear, that given access to f, we can create access to h. We know how to extend from f to h. So the 2 things I need to show is that the basic thing I need to show is basic step 3. I'll use 2 to prove 3. I need to show that the distance of h from G under the uniform measure exactly captures this distance from f to G under the mu measure. Again, once I show this property, then everything will hold from here. Okay, so this is what I'll show now.
So I guess, maybe it'd be fair if you say this is equal if you replace the u sub n with the mu to the k, and then you don't even need step 2, right? Part 2, just whatever mu to the k happens to be.
Good. Okay, so this if this was mu to the k,
No, to do that, you
now
u to the k is approximately u sub n.
So
But the two parts are independent.
so this is always going to be true if mu to the k was independent copies of mu, right? If mu to the k is k independent copies of mu, this thing is always going to hold, that if you know for any linear function g, the mu k distance of h from G is going to be the mu distance of f to G. Okay? And now if you can show that if mu k is super close to uniform, we can basically replace mu k with uniform everywhere and everything will still hold. Okay, so this is what we'll show.
And actually, I guess, sort of, once you have this fixed g, you're really sort of just talking about a fixed bit.
Exactly.
And you're just looking at independent copies of that
Yeah,
bit.
yeah, yeah. So these is very straightforward Fourier manipulation right now. There's nothing tricky left at all. I cannot, if I don't want it, if you can let me not talk about it, I can talk about something else which is also quite interesting.
Okay.
Yeah? So this is straightforward Fourier calculation.
Talk about both if you want.
So let's there's something very related. So these 3 steps, this distance exactly captures this distance and we're done. Okay? Okay, so another aspect of this let's look at. Okay, all these tests and local list decoders and all that, they were very query efficient. Okay, they made only poly 1 over epsilon number of queries, but the time complexity was terrible. All these worked in exponential time, like 2 to the n. The time complexity was as bad as the worst algorithm, the naive algorithm without locality whatsoever. So the time complexity was really bad. Okay, so is there any hope for the time complexity at all? Okay, so for special codes like the dual BCH codes, etc., we said that we could be a bit more. Those codes, you exploit the structure of the underlying distribution to come up with these correlations and be time efficient. But in general, it's very hard to say something about the time complexity. But what we do show is the following. We show that for these random linear codes, if you don't care about being local, okay, let's just try to be time efficient. Let's forget locality. Let's try to do the problem of local decoding or local list decoding of these random codes a bit more time efficiently. So the naive algorithm what would it do? How would it do the local decoding? It would run over all possible code words. So you're given a received word R, it would look at all possible code words and try to estimate the distance, see if R is close to C or not, and then hence estimate the distance. Okay, so that's exponential time 2 to the n. Can we do something a little better? Okay, so we do just a little better. So we give a sub-exponential time decoding, and this could be sub-exponential time, even list decoding from worst case errors. Okay, for unbiased codes. But these codes need not be sparse now, it's any unbiased code. And here what I mean is the weight against the weight of any code word C is basically half plus minus n to the minus gamma. Okay, take any unbiased code with weight half plus which is roughly balanced. We'll give time 2 to the n over log n time algorithm.
What are you assuming in terms of your access to the code?
So the code has dimension n, right? So what was n out here? So it was, the code was mapping n bits to capital N bits. So say capital N is like n square. So little n. So one interesting regime is capital N equal to n square, say. Okay. Take an unbiased code where you square the number of bits. So you can actually see the full code. You can see the generator matrix. You can see the received word. You're running in time, which is nearly exponential in little n. So you know everything about the code. And you are now given an arbitrary received word, you want to decode the code. That's the problem. Okay? So, but it's a random code. So again, we're doing slightly better than the naive algorithm. And the naive algorithm for decoding such a code would have been, the total number of code words is 2 to the little n. It would run over all of them and see if your received word is correlated to them or not. So we're giving an algorithm which is slightly better than naive. It's running in sub-exponential time. And the techniques we use for handling these codes is exactly the same as what we've just talked about all this. We're going to start with this code and we're going to somehow transform it to a question over the uniform distribution. Okay? But the way we transformed earlier questions over the uniform distribution, we lost, there was no hope. This back sampling was very, very expensive to query a particular point. We wanted to query lots of things from the earlier thing. We'll do this transformation in a way which will preserve this which will make back sampling easy. That's one thing, because we're given so much time. We'll do it in a way which makes the back sampling easy. And what do we reduce it to a question of is the problem of learning noisy parities in learning theory. So we're going to reduce it to that problem. So let me.
So are you going to have time to go through this in detail, or
So I won't go through.
to do this next week?
So there's not too much interesting stuff to say. In 5 minutes, I'll be able to say whatever is really new or interesting. Okay. Is that good? Yeah. So I won't give the proof. So I'll just. No. So there's not this. Okay. So let me quickly wrap up in a few sentences because there's not too much interesting to see here. So again, I'll take this code. I'll take this distribution, and I'm going to take lots of convolutions to reach to the uniform distribution. So this can be done. Okay. This code is not sparse. It will turn out that the Fourier quotients are not going to be as small. So constantly many convolutions will not lead to the uniform distribution. You have to take something like n over log n convolutions to reach the uniform distribution. Okay, but let's take that. We have a lot of time to deal with everything. So we'll take a huge number of convolutions and reach the uniform distribution. Okay. So basically taking n over log n independent samples from the distribution you get from here will take you to the uniform distribution. But how do you back sample? So Blum, Kalai and Wasserman, they gave an algorithm for learning noisy parities and cast in the language of codes. This is basically saying the Hadamard code has this property. The Hadamard code, it's not saying that the Hadamard code can be list decodable in so much time. It's saying that the Hadamard code can be list decodable in so much time with random samples to the code, to the received word, not with oracle access. You're not allowed to query it wherever you want. Then the Goldreich-Levin does it. If you're not allowed to query the function wherever you want, you're just getting random samples from a function, then that's the problem of learning noisy parities. So the Hadamard code is list decodable from random samples. They give a time 2 to the n over log n time algorithm for this problem. Okay. So now if you don't want to query the Hadamard code at any point you choose to, if you just want random samples, then the back sampling process is easy. Okay, so I started with the function f, I defined a function h. If I wanted to query h at the point x, then simulating oracle access to h at a point x was difficult because I had to query a very special set of points xi's in the f domain to be able to do this. But if I want to sample h at a random point, it's easy. So you just sample f at random points, and the sum of random of f evaluated at enough random points gives you h evaluated at a random point. So now transferring from f to h in this random sample language is very, very easy. To simulate oracle access, you can easily get oracle access to random samples of h given random samples from f. So the translation is the time, the translation of, so that we don't lose the time efficiency if you only care about random samples. Okay, so this problem about sub-exponential time decoding of random linear codes, we'll get a function, we'll convolve it many, many times. What will happen is when we convolve it many times, the error will, if the error will get really, really bad. So a linear function g, which was somewhat close to a linear function f, now when we convolve many times, that linear function g became quite far from the original, from the new function h, but we still want to recover the function g. And the time complexity, this huge time complexity, is going to be because we need to list decode from a much larger radius, a radius which is very, very close to half. Okay, but basically we take the code and we reduce it to the problem of decoding the Hadamard code from random samples. So I don't need to say beyond that. That's basic.
So there has to be some limit on the number of random samples you can sort of simulate in this, right? Or
there's no limit.
So as long as you're just random, saying as long as you're just random.
If I start from a distribution mu, I know that n over log n times if I convolve it, I get the uniform distribution, exactly the uniform distribution. So each sample now, each time I take now some n over log n samples from mu, I get a uniformly random sample from uniform.
As long as the number of samples is bounded to n over log n. Or is it?
Maybe large, at least n over log n, because that's when I reach the uniform distribution. Mu convolved.
Right, but then how many samples can you take from the thing that you reached?
How many ever I want to.
Presumably you can't reconstruct the whole thing, right? You can't go back for the entire.
Each time now, so if I know that mu convolved with itself m times the uniform distribution, I can keep sampling from the uniform distribution now by just taking m sample, take m independent samples from mu.
In the forward direction.
In the forward direction, I get a sample from the uniform distribution, and I can keep doing this. And I don't need to do the back.
So that's what I don't.
Because now what I want to do is just get uniform, to decode the Hadamard code, I just needed uniform samples from h. So I just need to go in the forward direction. I'm avoiding the whole thing altogether.
So why do you set up, because they always set up this log also?
So this error blow up, just this large number of convolutions. We'll eventually, this algorithm would have needed 2 to the n over log n, but our time complexity worsens because when we do this convolution to reach the Hadamard code, just the blow up in the error, that 1 minus epsilon and 1 minus epsilon to the k. When k is n over log n, this is too close to half. So the amount of error, so BKW takes 2 to the n over log n time in list decoding from a constant number of errors. But when the number of errors is very, very close to half, then the time complexity, this will become basically 2 to the n over log n. Okay, so I can stop here. Yeah.